In the last video, we talked about the standard form of a polynomial, how to recognize a polynomial, and how to determine its degree, and its leading term, leading coefficient, and constant term. Now we're going to talk about power functions. And a power function is just a monomial function in the form f of x equals a times x to the nth power. A is any real number not equal to 0, and n is any positive integer. So notice that we could also define a polynomial as the sum of power functions. So each term in a polynomial is actually a power function. So we're going to look at two different types of power functions. The first one we're going to look at is what we call even functions. They are things like x squared, x to the fourth, x to the sixth. So these are things that have even exponents or even degree. I shouldn't say even exponents, even degree. So if we look at these three graphs here on the left, let's see if we can figure out which is x squared, which is x to the fourth, and which is x to the sixth. So by doing that, I think we should plot some points here. X squared, x to the fourth, x to the sixth. And let's see, we'll do -2, -1, 0, 1, and 2. So x to the -2 squared is 4. -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. We should know that from the library of functions. -2 squared is 16, to the fourth, sorry. -1 to the fourth is +1. 0 to the fourth is 0, 1 to the fourth is 1, and 2 to the fourth is 16. Okay, x to the sixth. That's a little bit more complicated, and I hope you guys are using your calculator. But -2 to the sixth power is 64. So we would have 64. 1 to the sixth is 1, 0 to the sixth is 0, 1 to the sixth is 1, and 2 to the sixth is +64. So which ones are which here? Well, I think if we look, we can all agree based on the points -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4, that this solid graph is x squared. So there's our x squared. Now the question is, which one's x to the fourth and which one's x to the sixth? Well, the -1, 1, 0, 0, and 1, 1 points are not going to help us, because if you notice, all three of the graphs have these 3 points that I'm highlighting in yellow in common. But I think it should make sense to everybody that the one with the long dashes is x to the fourth, and the one with the short dashes is x to the sixth, because x to the sixth is clearly getting bigger faster than x to the fourth. So that's what these even functions look like, you'll notice they all kind of have the same basic shape as a parabola, even though they get a little bit rounder at the bottom the bigger the exponent gets. So let's answer these questions for our even functions. So I am going to color coordinate here. Our even functions, and this is for the even powered functions. Do they share the same shape? Basically, yes. Do they share any points? Yes, they all have -1, 1, 0, 0, and 1, +1. Are they symmetric to the y-axis, the x-axis, or the origin? So y-axis symmetry means if we fold it along the y-axis, do the two halves match up? X-axis is the same thing, but across the x-axis. So if we folded the paper along our x-axis, would the pieces of the graph line up? And origin symmetry means to get the pieces to line up, we have to fold it on the x-axis and on the y-axis. So hopefully we can all tell for the even functions, if we fold, and if you look at the graph, I'm drawing a dotted line on the y-axis. If we fold the paper along that dotted line, then the right half of the graph will be exactly on top of the left half of the graph. So these have symmetry to the y-axis. What's the domain? Well, they're still polynomials, and all polynomials have domains of -infinity to infinity. What is the range here? Well, the range is 0, including 0, because we have the point at the origin, and the y values keep increasing to infinity. Okay, now they want us to talk about the end behavior. And remember, the end behavior is what happens to the graph as the exponent increases and x gets closer to positive or negative infinity, as opposed to what happens if x gets closer to 0. So what happens is, as n increases, that's our exponent, remember, the graph is wider, or I should say the y values, sorry. Let's try this again. The y values get smaller as x gets close to 0, but the y values get larger as x approaches either positive or negative infinity. So for this first part, we are talking about this area right in here. And you'll notice that the larger exponent curves are actually below our x squared. So that is the y value getting smaller because it's lower when the exponent gets larger. When we're talking about the part at infinity or negative infinity, we're talking about the parts up here, where the arrows are. And as you can see, y gets larger faster as x approaches infinity. And we can see that in our table also. If we look at 2 for our x squared, the y is 4. For x to the 4th, it's 16. And for x to the 6th, it's 64. So hopefully that makes sense. In the next video, we'll look at the graph on the right, which will be our odd power function.